Welcome to this lecture where we will take a closer look at the concept of transport services and the transport services architecture, TAPS, that is currently under standardization within the IETF. My name is Anna Brunström, Professor in Computer Science at Karlstad University, Sweden. In this lecture, we will first briefly recap the problem of Internet ossification and the various solutions that have been proposed to deal with the problem. We will then take a closer look at the concept of a service-oriented API for transport protocols, and then look into the transport services architecture, TAPS, that is now being standardized. And finally, we will summarize the main points of the lecture. First, recall the problem of Internet ossification. As we discussed in our last lecture, the Internet was originally designed in a layered fashion, having the IP protocol as a thin waist, with the idea of supporting a multitude of protocols and services above. However, as the Internet has evolved, the TCP protocol has been extremely successful and is today the majority of the traffic. We have also seen a boom of web applications where most of the traffic today is HTTP over TCP. When you have a traffic that is very common and very successful, the network elements start making assumptions about the traffic. And today we have a large number of middle boxes on our end-to-end communication that may interfere or interact with the traffic. And these middle boxes expect the traffic to be TCP or HTTP. Due to this assumption, it is today very difficult to introduce new protocols over the Internet. So the Internet architecture has ossified, where it's today difficult to send anything but a web-based client-server traffic across the Internet. This problem has been further worsened by the success of the Socket API. The Socket API does not offer much flexibility, and it directly ties the protocol to ties the application to the protocol. So if we now have to decide on the protocol at the time of design, and TCP is the protocol that we know makes it through most of the network, well then it's very easy to make this choice. So we will pick TCP, and new and perhaps better protocols will not come into use. So what are some ways that we can try and overcome this problem of ossification? Well, we can try and extend TCP with new services, as is for instance done with the multipath TCP, MPTCP, but this is still difficult and we have to conform to the various assumptions that middle boxes make on TCP traffic. We can also try to build new protocols atop either TCP or UDP, which is the other protocol that may make it through the network. And this is the approach taken by the QUIC protocol that is currently under standardization. QUIC runs on top of UDP and therefore looks as UDP traffic to the network. If we want to communicate in a peer-to-peer fashion in the network, there are also techniques and protocols to try and deal with the firewalls and nets that our traffic may have to go through, and that is very difficult today when we assume a client-server model for the traffic. We may also have techniques to try and determine what our end-to-end path supports. And this is important when we try to use a new protocol in order to be able to detect if this protocol actually works, and then being able to fall back to alternatives if the protocol is not supported. And this is, for instance, used in the happy eyeballs mechanism, which is a standardized way of selecting between IPv6 and IPv4. And we may also have an approach where we look at the more expressive API that allows us to express the services we need in a different way. And this is the approach taken by the TAPS API and the transport services architecture. And in this lecture, we will focus on transport services and the transport services architecture that offers such a more flexible API and that also incorporates the mechanisms for a generalized happy eyeballs and selection mechanism. And of course, underneath such an architecture or within such an architecture, We can also make use of the new protocols that are being developed. So this is one of the goals of the TAPS architecture. So let us first look at the general principle behind a service-oriented API for transport protocols. So as I just mentioned, the socket API, which is today used by most networked applications, does not offer much flexibility. In practice, it directly ties the application to a protocol. So even if it's in principle a generic API, where you, for instance, ask for a SOC stream, and this could be mapped to any protocol that provides a reliable ordered stream, in practice, you will be given TCP, and you will have other parts of your application code that directly ties you to the protocol through, for instance, a number of socket options. So you will have in your code, for instance, a call to set TCP no delay to turn off the Nagel algorithm in TCP or perform any other configurations of the protocol. And this ties your code directly to a particular protocol, and it's not easy to use a new protocol in this context. So a service-oriented API adds a layer of abstraction. And the idea with this is to decouple the application from the protocol, and hence making it much easier to make a dynamic selection or to introduce new protocols. And the idea of this is illustrated in the figure to the right. So we have, as usual, the application on top, but instead of directly communicating with the protocol, we communicate with the Transport Services API, an abstract representation of the services that the underlying protocols can provide. And then we have an implementation of the Transport Services systems that then provides the mapping between what the application requires and to the available protocols. So you have some transport service selection and setup provided by the Transport Services implementation. And this implementation could then use a multitude of different protocols underneath. It could use a TCP or a MPTCP or a new transport protocol that resides in the kernel, or it may also use some user space implementations of protocols such as SCTP running on top of UDP, or some new transport running on top of UDP such as the QUIC protocol. And then underneath you have the network layer with IPv4 and IPv6. And the idea of this abstraction that we have in the Transport Services API is then, of course, as I said, to decouple the protocol from the application and allow this selection to be made dynamically and allow new protocols to be introduced. The idea of a service-oriented API to the transport system is not a new idea. That has been suggested in the research literature a number of times over the years. However, it has never taken up within industry. What is different now is that we see an ongoing standardization of a transport services architecture within the IETF, bringing this into potential mainstream. And we have companies such as Apple and others directly involved in the process. So what does the Transport Services TAPS architecture then provide? Well, it provides such a common service-oriented, flexible and reusable interface for the transport protocols. And underneath this API, you allow a multiple of IP addresses, a multiple of protocols, or a multiple of paths to be used. So we can now make a dynamic selection. And the transport architecture underneath the hood then supports the applications with raising and fallback mechanisms, raising to select a suitable protocol for the services that have been requested, and also if you try out the protocol that doesn't work, it will automatically fall back to another protocol. And this dynamic selection allows then to dynamically optimize the selection of the transport service realization, and this is based on the application requirements. It may also take the network conditions into account, and it may use system policy. So based on all these three inputs, the transport services architecture will set up a suitable transport connection for the application. And this, of course, also then enables deployment of new features and new protocols. Because as these connections are dynamically set up, when new protocols and new features come available, they can be used immediately without the need of rewriting applications. Let us have a closer look at transport services architecture in graphical form. So the application on top will communicate with the transport services API. And this communication goes through 4 phases. We have the pre-establishment phase. This is when the application conveys its requirements for the communication to the transport system. We then have the establishment phase. This is when the connection used for communication is set up. We then have the data transfer phase. This is when we are reading and writing our data over the connection. And then we have the termination when we close the connection. And the Transport Services API is an asynchronous event-driven API. So we receive a number of events to the application, for instance, when there is data available for reading or when a send operation has completed. So the Transport Services API has a few basic objects that are manipulated through the application. So it has a pre-connection, which is the object used to set up the different requirements from the application and store these requirements. Once you establish the communication, we have a connection object, which is then the object used for sending and receiving the data. There is also a listen object for setting up a passive connection. And underneath the Transport Services API, we have the Transport Services implementation. And this implementation is then responsible for the candidate gathering and the candidate raising. So based on the requirements that the application has provided to the Transport Services system, the Transport Services implementation will identify the possible candidate protocol stacks that can realize this communication, and it will then perform a generalized happy eyeballs mechanism or a candidate raising to determine which protocol to actually use. And here we may try multiple protocol stacks in a varying order depending on the requirements that we have received from the application. And in this decision process, we may also make use of cached state, things that we have learned about the network or the path through previous communication attempts or through some other means. And we may also have some system policy that influences how the selection is made. The system policy may, for instance, say that we are required to always use a secure communication, or it may specify other preferences. And underneath, of course, we have the protocol stacks that then realize the communication to the application. So let us look at an example for how a transport stack is selected in a TAP system. So as I mentioned, the application specifies its requirements to the TAPS system during the pre-establishment phase. And this is done by the application specifying a number of transport selection properties. And these properties can be specified at different preference levels. So an application may require a property, it may prefer some property to be used, it may like to avoid some property, or it may prohibit the use of some properties. So to take an example, the application may require reliable transfer, it may require ordering to be preserved, it may prefer to use a Wi-Fi interface if available, and it may prefer to use multipath communication. So let's look at how that may be mapped into a communication system situation where you have a client connected over a Wi-Fi and a cellular path to the internet, And you have multiple protocols available underneath. You have an MPTCP protocol, you have a TLS over MPTCP, you have QUIC, and you have TCP or TLS over TCP as possible choices here. And you then also have choices related to the interfaces. So as multipath is a preference, the TAP system would first try to use a multipath protocol. In this case, it would try MPTCP or TLS over MPTCP, which provide all the requirements of the applications and also matches its preferences. And if it succeeds with MPTCP, it will also try to set up the connection over the Wi-Fi interface, the initial subflow of MPTCP, as the application prefers Wi-Fi. If MPTCP is not available or does not make it through the network when we try to set up the MPTCP connection, the system will fall back to some other alternative. So maybe it will now try QUIC. If QUIC does not work, then it will try TLS over TCP or TCP, and in both cases it will start to try these protocols over the Wi-Fi interface, as Wi-Fi was preferred by the application. If neither of these work, then it will start to try those protocols over the cellular interface. And as Wi-Fi was just a preference, it is possible to also communicate over the cellular interface. If instead the application had the required Wi-Fi, then only this interface would have been allowed, and this of course would have restricted the choices. We may also have other factors, as I mentioned, that influence the choice. So let us assume that the application did not give a preference for what interface to use to start with. We may have cached information that tells us that Wi-Fi has a better communication quality than cellular, and this may then prompt us to start the communication over Wi-Fi. Or we may have a system policy that says we prefer Wi-Fi over cellular because Wi-Fi is the cheaper path and we prefer to use that as much as possible. So in the particular example here, we only had the requirements from the application, but you can see that what happens if we change some of them and how we can also add preferences based on the policy and knowledge from how the network surroundings are. So let us summarize what we have covered in today's lecture. We have seen that the success and design of the socket API is one contributing factor to the problem of internet ossification. As this API is not very flexible and it in practice directly ties an application to a protocol, this makes it more difficult to introduce new protocols on the internet. And if you only have one choice, you will pick the protocol that you know works everywhere, reinforcing the use of a single protocol selection. We have seen that the concept of a service-oriented API and the transport services TAPS architecture aims to alleviate this problem. So the TAPS architecture is currently under standardization within the Internet Engineering Task Force, IETF, and it provides a common service-oriented interface to applications, and this decouples the application from the protocol used. So the TAPS architecture or the system implementing the TAPS system will make the selection of the protocol based on the application requirements, knowledge about the network surroundings, and any local policy. So the system integrates the raising and fallback mechanisms within the implementation, thus alleviating the application from this burden and making it more easy to use new protocols and to dynamically tailor the communication to different communication situations.